last talk of the day. Any energy left? Okay, so I'm here today to talk about what we are focused on for using AI for kernel generation. So the main objective is to leverage AI for building faster AI. So I think we all have been in this situation that we are dealing with AI workloads that are slow, whether that's training a language model or maybe an AI development from scratch. But we have to wait for a long time. That's a painful process. Now, behind the scene, what's happening, there are small programs called Kernel that they're doing the heavy lifting. And maybe sometimes, thanks to them being slow, we have option to go have some sleep and come back at the morning. So when we are dealing with the kernel generation, we are not dealing with Gordon Ramsay to yell at us. We have a lot of tiny chefs that are supposed to work together, and which is in this context, numbers are basically our materials, recipes are operation, and the meal that we are getting are the results out of the kernels. But the issue is that sometimes they're not working together. We have chefs that they're bumping to each other. They're waiting for each other to be free of the oven so then they can pass the information. And that's where we want to have a magical kitchen that everyone works together in a perfect sync and passing the information. So now the way that we generally go through this spectrum, we always start with naive kernels that probably they are slow, dependable, and they're not using the hardware to the max capacity, but maybe they will be eventually there. And now what our kernel engineer does, they're basically handcrafting all those kernels for the maximum capacity and usage of the hardware. But what we are dealing in this industry of AI, everything is changing super fast, that we want to have a system that can auto-tune itself based on the hardware is being used on. So that's the recipe that we want to have. So now, when we think of it from the perspective of what kernel engineers do, they're tweaking assembly code, they're counting cache lines, and they're managing memory. But the issue is that it's like a speed dating. Either you get it right fast, or the demand is gone. And also, probably they live on a huge amount of caffeine. And sometimes I think that maybe Red Bull starts to kind of sponsor our kernel dev community. But now the point is that what we want to go for is an AI system that can self-reflect and optimize the performance on the hardware is being used. So how we can leverage on that, it's using LLM to generate a lot of candidates and then measure the performance and mutate and refine them. You can think of it like a Tinder. Swipe left when you get a bad kernel, swipe right when you get a good kernel. And hopefully at some point you see your soulmate, a beautiful 200 T-flops of best performance. So now why this is important? This statement from Dario is probably a couple of months old already, but we are reaching to the point that a lot of code is being generated by AI. But the issue is that we are right at the corner of explosion of the volume of AI-generated code, but the main issue is that it doesn't have a depth. It doesn't know how to use the hardware. Writing a Python code is something. Having a code that knows how to use the hardware to the max extent is something else. So that's our objective. We want to build a system that we can get any Python code or any kernel code and optimize it, so then we can leverage the maximum capacity out of the hardware. What is our scoreboard? Is a roofline. So we want to know whether we are either compute bound or memory bound to know in which direction we need to move. But the main issue for dealing with these kernels is that we don't have a huge amount of open source data. So we need to rely on a lot of manually generated code, or we find a way to massively produce these kernel codes. That's what we were trying to do. So what we would do is that we are using our agentic frameworks to generate a lot of potential candidates for the kernels, and have our SMEs auditing the codes, and till we have a trusted optimized kernel that we can rely on for fine-tuning language models, so then eventually we use them for kernel generation. So this is agentic framework that we have. To begin with, we capture any code, whether that's a Python or a kernel in a heap, And the beginning of the process is the code analyzer. You can think of it as like a detective that goes inside the code, figure out what the code does, what are the shortcomings, and where are the rooms for improvement. Then our researcher goes to the documentation, GitHub repos, and identify the patterns for how to optimize the potential kernels that we have. And then the kernel generation will kick off. That will generate a lot of candidates, and that goes through the evaluation scheme that can start with the compilation. Do we compile the code? Do we have a correct output out of it? And if all those two pass, then we will go for a performance measure. And then independent of whether we have a successful kernel or not, that goes through the data collector for downstream reinforcement learning. But the job of the feedback analyzer is to look at all those generated kernels with all the feedback it has, whether it compiled or not, whether it passed the correctness, or if it passed the correctness, what was the profiling measure. All those get back to the kernel generation for mutation. But the kernel generation itself can evolve. We have a team of experts, like with the different reasoning capability, that each of them looking at the kernel generation from different perspectives. But at the end, we want to have an agentic framework that can generate enough sample for the kernel, so then we can use it for any downstream fine-tuning. So the tool that we have, we're calling it AGIKIT, and it's being used internally, and hopefully at some point we will release it. So now what this one does, it's grab a PyTorch code and generate a heap kernel equivalent of it for allocation of the memory, making sure that the computation is tiled, and making sure that we are using maximum capacity out of the kernels. So in order to kind of identify what are the best candidates, we have to come up with some sort of a scoring mechanism. So obviously, we start with whether those kernels are getting compiled. We allocate some score for that. If it passed the correctness, meaning that the output of the PyTorch matches with the output of the heap kernel with the threshold that we are considering, that if it's within the threshold, then that will get the score. And depending on what type of speed up we have, then we can identify what is the scoring mechanism. So for instance, if we have twice the speed up, then we allocate 200 a score, and if we have a 0.5 speed up, that will be 50 a score. But at the end, what matters is that we want to see accumulatively how we can improve the kernels. So the test that we have done to begin with was a level 1 kernel bench from Stanford. And here we can see a cumulative score that we got from different models. And this is only using those models without kind of evolving them across multiple models altogether. But now, if we want to identify which model perform what, obviously when we start catching the models with the score above 20, that means that they passed the compilation. So we can see that majority of the model got plus 80% compilation rate. But when we go to scores above 120, that's where that they compiled and also passed the correctness. So most of our model kind of sit within the 60-70%, except obviously the Qwen30B billion parameter model, which is quite smaller than the other. But when we go to a score above 220, which is basically we have some level of a speed up, that's where we can see that some reasoning models like GPT high and medium have a better chance to survive through this whole process. Although this PyTorch to heap is a good kind of data set generation process, but that's not something that we can immediately use for our production. That's why we started to focus on actual ROCm libraries, where we focus on kernel generation stack, like heap-blast-lt for gem and composable kernels for custom routines. And if we continue this process, we will hit ROCsolver and ROCblast, which is what we started to dig into. So ROCblast is basically three ROCm library that focus on the basic linear algebra in 3 levels, starting from vector to vector multiplication to matrix to vector and all the way to matrix-matrix multiplication, which each has a 58 API entry point. And for ROCsolver, which sits on top of ROCblast, we have 150 lab-back functions, which their objective is to rely on those basic linear algebra and perform tasks like decomposition or QR decomposition or LU caching. But the main issue when we are dealing with the library scale kernels is that we cannot have a standalone kernel because there are lots of interdependency. That's why we started to do a lot of depth-first searching to bring all the relevant source files, target function, to make sure that we are building reliable context for LLM to look at and generate candidates for optimization. And since building and compiling library scale kernels will take some time, so we injected a lot of C caching and compilation caching, so we save time when we are doing the iteration of the LLM. And then obviously we would use the correctness command, which is basically the test that our basic kernel engineers put together for rock solver or rock class. And at the end, we are using ROC-prof compute to close out the loop and get the performance out of each of the candidate that is getting generated. The outcome is that we are targeting a lot of source files that help to affect a specific kernels of interest. So for instance, when we look at what we got through rock solver, we target the 28 interface, meaning 28 kernels from the rock solver, and that resulted in modifying 284 target functions. And the outcome that we had based on the optimization that LLM gave us, we had above 90% compilation success rate, around 77% compilation plus correctness test, and then almost half of them had some level of improvement in a range of 4% all the way to 20.8%, with a medium to be around 5.75%. This is moderate, but this is at least showing us that's the first step in the right direction. And let's just not forget that we are doing this to put the data set together for our fine-tuning process to be the language model that is capable of doing this stuff. So that's our objective. So grab all these data, whether that's generated from the PyTorch to heap or from heap to heap from our ROCm libraries, and build a good data set that we can rely on. And that's where also we are doing a lot of collaboration with other teams, like the team of the Geek agent, that we are bringing the data set together so then we can start doing the tuning process. So this is our first result that we recently got using the data set that was generated. Again, this is the beginning. We are feeding and generating more data to bring it back to the SFT tuning process. And our initial results show that with a small 7 billion parameter model, we can generate torch to heap tasks up to 40% performance regarding the passing the compilation and correctness, and also the score, the F1 score that we have with respect to the training. But the situation for the heap to heap is a bit different because we have less amount of data, so it has almost half of the performance of the torch to heap. But at the end, what we are looking for, we want to build this ecosystem of agentic framework that we can generate data and pass it to the fine-tuning pipelines. So at the end, what we care about is to build a workloads that they can adapt themselves running on the hardware, depending on hardware that they're using. So then we can rely on AI to self-optimize for itself. And it basically evolves in the real time, so it's not frozen only to the compilation time. And then we can have machine that translate their own workload to go faster and utilize hardware to max capacity. And maybe next time that we go coffee, they come and drink coffee with us. And lastly, I want to give a big shout out to the whole team. This is not about one single teamwork, so there are lots of teams that are working on this. I just wanted to make sure that I give big shout out to different teams that are working on this. Thank you.